Now we're going to discuss an example of theory propagation implementation. In particular, we will choose decision procedure for theory of equality and uninterpreted functions. And since we need to provide a proper API, so we will show implementation of four of these functions: push, pop, checksat, and unsat code. So let's look at push. We have in the previous lecture discussed increment EUF, which corresponds to the push, and this is not a coincidence. It's a deliberate design choice, and we defined increment EUF in a way such that it can be used in for the push. And you may recall it had a global variable called conflict found, and if checksat is called, then we can simply look at this variable and say that the conflict has been found or not. Furthermore, you can implement pop, in which you need to keep the record. Recall that we had been keeping some record of merger of classes inside increment EUF, and what we need to do is when you pop an equality, you need to undo all these mergers that were done because of addition of these equalities. We leave the exact pseudocode for as an exercise. Let's look at the final function of the API, unsat core. When you call unsat core, you expect the formula already unsatisfiable, and we're going to collect all the literals that were involved in unsatisfiability. Remember that we had the theorem proven in the previous lecture, in which we showed that in any unsat core of equality reasoning, you have one disequality and others are equality involved. First, we will find a disequality that was involved in producing the violation. Let's suppose T1 not equal to T2 is that disequality. We say, okay, this guy is going to participate in unsat core certainly, and then we try to get reason what makes T1 and T2 equal. So let's collect those reasons. So there's a function which tries to find what makes T1 and T2 equal. T1 and T2 some point of time must have become a part of same equivalence class. Let us suppose T1 prime and equals to T2 prime be the equality when it was pushed, and that triggered a merge operation that made T1 and T2 belong to same equivalence class. So there are two ways it could have happened. One is that this is part of the input. Okay? So T1 prime equals to T2 prime was an input, and it came in and you may merge them. So therefore you can add as a part of a reason. On the other hand, it can be the case that this T1 prime equal to T2 prime is a recursive call, and a congruence axiom was applied, and you had a recursive call. So in that case, you need to show that why T1 prime T2 prime become equal, because S1 U1 were equal, S2 U2 are equal, SK UK are equal. So you need to collect reason why each of these Si and Ui became equal, and collect all those reasons and return the set. Finally, you have the case that the T1 and T1 prime must have belonged to the same equivalence class, and you need to find the reason why they become equal, and you have also earlier collected reasons, and similarly T2 prime and T2. We have shown you the implementation of four functions that needs to be available to implement theory deduction for a particular theory.